And this term is usually negligible. All right, so let's look at what happens as we change temperature to the equilibrium constant. So if delta H of reaction is greater than 0, so is it exothermic or endothermic? Endothermic. And we increase temperature, what happens to the equilibrium constant?
How did you get from the middle equation to the bottom equation?
This is this derivative if you make this assumption. And so essentially you end up with just Van't Hoff, but you have this extra term if you're doing it in terms of Kc.
That equals the left side dln of k over dt?
No, sorry, that's where we messed up. I'm just talking about this term.
Oh, okay. Oh, okay.
So this comes from Van't Hoff, right? And then what is the rest of this? It's just this term, so sorry. That's the one for Kc, which again is the one that we care about when we're talking about rate equations, because that's how we solve them in terms of concentration. But yeah, back to the question. If I increase the temperature, does the equilibrium constant go up or down? Goes up. Meaning you favor products. Does that make sense? Think about it, right? I need temperature to make the reaction go forward. If I increase the temperature, I make more products. Okay. And then, obviously, I can change all the signs. If I increase temperature, the equilibrium constant decreases. No.
Which formula? Are you looking at the top formula or the bottom?
You don't need to look at the formulas to do it, but it's this one. But no, it's the same. I'm increasing temperature. So an exothermic reaction, it wants to give off heat, right? It doesn't need heat. Heat is not a reagent, if you want to think of it that way. I mean, that's almost the way that you can think of these things. That you have A plus B plus heat goes to C plus D. So this is an endothermic reaction, right? It requires heat to go forward. So if I put more heat into the system, I shift equilibrium that way. Just like if I push more A or B into the system, I also shift equilibrium towards the product. And then if heat is, instead of being a reagent, heat is a product, then the opposite is true. As I push heat into the system, I push backwards. So it's the same as Le Chatelier's principle, but only with a pretend reagent or product, which is now heat. But the principle still works. So it's an easy way to remember.
What's the word that you wrote under that inequality over there?
Usually.
And that's only for an exothermic, right?
What do you mean?
The if statements.
Yeah, I mean, this is saying if it's endothermic, then increasing
Okay,
temperature
gotcha.
will increase.
Yeah.
If it's exothermic, increasing will decrease.
Gotcha.
So what we can use this equation to do is if we take the ratio now of two equilibrium constants at two different temperatures, that's what we get. And remember, if we assume that the delta H of reaction is essentially constant, over the delta T that we care about, meaning T1 minus T2, T2 minus T1. Then you can come back up here and you get and again, this term is usually small compared to this term.
You wrote delta x, delta HRx is a function of temperature. Oh, never mind, I said it. Never mind.
Okay, so let's look at so that's equilibrium conversion, little e, which is a function of temperature. So, for example, if we have A to B, non-isothermal PFR, negligible pressure drop, no inlet flow of our products. So the equilibrium constant, KC, is equal to what? Concentration of the products over the concentration of the reactants, all raised to the stoichiometric coefficients. And again, to avoid confusion, we can put little e's in there, because it's not like this is always true. It's certainly not true at the inlet of the reactor where there's no B, right? It's only true when these concentrations that you're putting in are the equilibrium concentration. And delta is equal to 0 for this problem. So epsilon is also 0. And so if we go now to stoichiometry, we get the concentration, it's the flow rate divided by the volumetric flow rate. So how does this formula simplify? Pressures are approximately equal to each other. What else? Epsilon is 0.
I thought you said it was ideal gas. Oh. Epsilon is 0.
Yeah. And we'll put in the definition of our inlet concentration as well. And then what is it for CB? Because we need that now. It shows up in the definition of our equilibrium constant. Is that all, Adam? Yeah, that shows up as good as well. Okay, so plugging that into, we can do that over here. Let's plug that into here. Ca naught